Welcome to this explainer. Whenever we think about life-saving pharmaceuticals, we usually picture clean rooms, sterile gloves, and those high-tech microscopes. But there's actually a massive, complex, and completely invisible shield protecting all of those medicines from contamination. So today, we're going to demystify the hidden world of pharmaceutical HVAC systems and look at how strict regulatory audits keep all this invisible machinery in check.
Here is our roadmap for today. We'll start with Section 1, the Air Quality Imperative. Then, Section 2, Types of HVAC Systems. Section 3, Anatomy of the AHU. Section 4 covers the filtration hierarchy. Section 5 is ducting and air distribution. And finally, Section 6, Auditing for Compliance.
All right, let's jump right into Section 1, the Air Quality Imperative, setting the baseline for pharmaceutical manufacturing.
Now, you've probably got an HVAC system sitting in your own home, right? But in the pharma world, it's defined entirely differently. Yes, it still stands for heating, ventilation, and air conditioning, but it operates as a rigid environmental control system. It maintains highly specified temperature, humidity, air cleanliness, and pressure differentials in those manufacturing areas. The absolutely crucial point here is that in pharmaceutical manufacturing, HVAC isn't just about keeping people comfortable. It is a strict regulatory requirement to ensure product quality and compliance with good manufacturing practices, or GMP.
So, what are the core functions here? Think of these as specific layers of defense against dangerous manufacturing threats. It controls temperature to protect highly sensitive chemical substances. It develops differential pressure and maintains proper air movement, which basically means it dictates exactly which way the air flows, so contaminants literally cannot push their way into clean areas. It manages air quality and filtration by aggressively stripping out airborne bacteria and dust. It controls humidity, and ultimately, it prevents cross-contamination. Every single function on this list is a critical shield.
Moving on to Section 2, Types of HVAC Systems, Ducted versus Non-ducted Architecture.
Okay, let's zoom out a bit. In pharma, HVAC architecture is fundamentally divided. You have your massive, facility-wide ducted systems, which come in two main flavors. First is the chilled water system, where a chiller cools water that's then piped all the way across the facility to the air handling unit for heat exchange. Second is the direct expansion, or DX system, where refrigerant circulates directly inside the cooling coils. Now, on the other end of the spectrum, we have smaller, localized, non-ducted systems. This includes standard window systems packed into a single box for one room, and split systems, which separate the indoor cooling coil from the outdoor compressor. But for large-scale pharma production, those big ducted systems are the absolute heavy lifters.
Section 3, Anatomy of the AHU, the heart of the building.
If we think of the facility as a living organism, the air handling unit, or AHU, is its beating heart. Let's trace a single breath of air through this system. First, it enters the mixing box to blend fresh outside air with return air from the building. Then it hits a coarse pre-filter, typically a G3 or G4 grade, to strip out large debris like pollen or bugs. Next up, a finer bag filter, graded F7 to F9, catches microscopic particles like tobacco smoke before the air sweeps over the cooling and heating coils to reach the exact right temperature. Finally, the blower fan forces this pristine, conditioned air back out into the facility.
Now, cooling and heating coils do exactly what you'd expect. Cooling coils use chilled water or DX refrigerant, while heating coils use indirect hot water or direct electric and gas heat. But handling excess moisture, that is where things get really fascinating. To dehumidify, the system actually overcools the air all the way down to its dew point. It literally wrings the water right out of it, forcing condensation. Then it uses a reheat coil to bring that air back up to the desired supply temperature, just without the excess moisture. It's a highly engineered, brute force process. Conversely, if the air is too dry, humidifiers step in to restore moisture using high-pressure spray, a steam pan, or a steam grid.
You might be wondering, why does moisture control matter so much? Well, operating outside the ideal relative humidity range of 40 to 60% introduces severe biological and mechanical risks. In that sweet spot, humans are comfortable, and the risk of bacteria or viruses is low. But if you drop below 30%, it's way too dry. You get respiratory irritation and static electricity, which is incredibly dangerous around sensitive electronics and volatile chemicals. Go above 70% and it's far too humid. You risk rapid mold growth, condensation on the walls, and massive bacterial proliferation. A humidity failure is, without question, a GMP failure.
Which brings us to Section 4, the filtration hierarchy, the kidneys of the system.
If the AHU is the heart, the filters are the kidneys, constantly pulling dangerous toxins out of the building's bloodstream.
Filtration is essentially an escalating war against microscopic threats. At the base level, standard EN 779 filters, ranging from coarse to fine, catch everyday pollen and dust in standard labs and offices. But cross into critical cleanroom territory, and we escalate to EN 1822 aerosol filters. This includes E10 to E12 HEPA filters for ISO 7 clean areas, and the famous HEPA filters, H13 and H14, which are the absolute standard for high-requirement pharma and hospitals. At the very pinnacle are ULPA filters, or ultra-low penetration air filters. Graded U15 to U17, these are required for the most extreme ISO 4 to ISO 2 cleanrooms, featuring the strictest leakage rules in the entire industry.
All right, Section 5, Ducting and Air Distribution, the veins and arteries. Once that air is perfectly filtered and conditioned, it's got to be safely transported, right? The breathing cycle of the building requires both delivery and extraction. On the delivery side, the fresh air duct, or FAD, pulls outside atmospheric air into the AHU. After conditioning, the supply air duct, or SAD, delivers that pristine air to the manufacturing areas. On the extraction side, the return air duct, or RAD, operates at a slight negative pressure to pull air from the rooms back to the AHU for retreatment. Finally, the exhaust air duct, or EAD, grabs heavily contaminated air from places like labs or toilets and vents it safely, directly outside.
Now, choosing your ducting material is a real balancing act between safety and your budget. Galvanized iron is cheap and easy to fabricate, but it rusts in high humidity. Aluminum is great for resisting moisture, but it definitely costs more. Fiberglass absorbs sound beautifully, but it shakes violently at high air speeds. And then there's stainless steel 316L. This stuff is practically indestructible and highly corrosion resistant. Sure, it will completely destroy your budget, but it remains the absolute gold standard for pharmaceutical environments.
Down at the actual room level, the hardware totally dictates the airflow, and the mechanical differences here are super important. A grill is a fixed opening primarily used for return air, and it's purposely left without a damper to ensure that airflow back to the system is never restricted. A register, however, includes a damper, so operators can dial in the exact supply volume with adjustable blades. And a diffuser does exactly what it sounds like. It discharges and spreads supply air wide over an area to prevent drafts and noise from disrupting sensitive equipment. Finally, we hit Section 6, Auditing for Compliance, Evaluating the Invisible Journey. Here is where the rubber really meets the road. All of these mechanical parts we just talked about mean absolutely nothing if they can't pass a rigorous regulatory audit. During an audit, inspectors are literally hunting for mechanical failures they can translate into compliance violations. They don't just look at the machinery, they demand approved qualification docs, design, installation, operational, and performance alongside current SOPs. They'll demand proof that all temperature, humidity, and pressure sensors are perfectly calibrated. They verify HEPA filters have passed specific integrity tests like DOP or PAO. They check the pressure cascades and air changes per hour match the specs, and they will rigorously test for zero air leakage from ducts, joints, or dampers.
Take a look at how an 80-point audit is weighted. The regulatory burden is actually incredibly lopsided. The production zone alone commands a full 20 of those 80 points, or 25% of the total score. And honestly, that makes perfect sense, because this is the critical area where the product is actually exposed to the environment. General system compliance takes 15 points, chemical substances manufacturing takes 13, the warehouse takes 12, and quality control and assurance take 10 points each. These points literally dictate the ultimate fate of the facility. Score 90% or higher, and you're rated excellent. Drop into the 75 to 89% range, and you're going to require immediate corrective actions to fix a system that needs improvement. But a score below 60%, that's designated as a critical failure. It means the invisible shield is fundamentally broken, and product safety is officially compromised.
So I'll leave you with this one final thought to chew on. If a single invisible particle can completely compromise a life-saving medicine, how confident are you in the invisible systems protecting your environment? It takes a massive amount of silent, mechanical vigilance, paired with totally uncompromising regulatory audits to keep our medicines safe. Thanks so much for joining me to explore the vital, hidden world of pharmaceutical HVAC systems.